Hi, welcome to the second video on the Analytic Geometry series. Last time we're talking about the circle as one of the conics. This time, we'll be talking about one of the conics, which is a parabola. So, what is really a parabola? So, if you would like to imagine, a parabola is a graph which is a mirror symmetrical and it's almost a U shape. It's something like this. This is a parabola. So it's either your parabola opens to the right, or it opens up, or it opens down, left, sorry, or it opens down. It depends on the behavior of the equation. So the point at which the graph attains the maximum and the minimum level is actually the vertex. So here's the minimum level of the graph, or the maximum level of the graph. So something like that. So this time we'll be talking formally on what is really a parabola. So this time we will be talking about the formal definition of a parabola. As I mentioned earlier, a parabola is one of the conics. Yes, because it is created by the intersection of a right circular cone and a plane. So that plane is also parallel to another plane that is tangential to the cone. So to formally discuss that, we are going to tackle the formal mathematical definition of a parabola. A parabola is a set of points equidistant from a fixed point called the focus. So in plural, we call this as foci. And a fixed line called the directrix. So in other words, if you have a graph of a parabola here, let's say this is a parabola, so it's if the here somewhere here is a focus of the parabola, and somewhere here is the imaginary line or the directrix of a parabola. So according to the definition, if you pick a point here on the parabola, the distance from this point to this point is the same as the distance from this point to this point. Although it looks like it's not because my graph is not perfect, or my drawing is not perfect. But technically, that's what the definition tells us, that if you found a point, the distance from this point to the focus and the distance to the directrix are actually the same. Okay, this time we're going to discuss about the components of a parabola in order for us to graph a parabola easily. Although we have been given a set of equations in high school, we're asked to plot or sketch the graph of those equations. Some of them are actually parabola. I don't know for some reason why some of them are not named as parabola, but actually those parabola can be plotted easily without just our traditional making initial points. Say for example, back in high school, if you're going given an equation, you'll have to assume a value of x, then you get the y, and so on until you get an initial of at least 10 points, and those 10 points you can plot them on the graph, then follow the sketch, something like that. Now this time we're just going to master the component. We're going to easily identify those equations if that's a parabola, opens up, opens down, and so on. So let's discuss this first. So this is your parabola. Suppose this is your parabola. So a point at which the parabola attains its maximum or minimum value is called a vertex. So this type of parabola attains the minimum value. So this somewhere here, the minimum value is the vertex. Excuse me. Since a vertex is a point on the parabola, and according to the definition, a parabola is a set of points equidistant to the focus and the directrix. So if this is your focus here, somewhere here is your directrix. So the distance from this is equal to this. Another part is, although it sounds funny to you, but this is quite important, the latus rectum. Which means this is an imaginary line segment connecting from a point on the parabola to the other point on the parabola, passing through the focus parallel to the directrix. So this point here, going to the other point of the parabola, passing through the focus, and this line segment is parallel to the directrix, then this is your latus rectum. This is quite important because this will tell you how wide your parabola is. By simply getting the vertex, getting the focus, getting the latus rectum, you can connect this to this and continue that way. You can connect this to this, continue up, something like that. That's how easy to graph a parabola. So here in this case, the length of the latus rectum is measured as 4p. Your p is some positive rational number. And if you divide 4p by 4, you'll get p, of course. This will tell you the distance from the focus to the vertex, or the vertex to the shortest distance from the vertex to the directrix. That's it. Now, we're going to derive an equation of a parabola. So I'll just reconstruct this one. Sorry. So assuming again this is your parabola. So this is your vertex at point, let's say HK. So somewhere here is your directrix. So somewhere here is your focus. Your focus should be aligned to your vertex. So therefore, the point here is the same, has the same x coordinates. So I have here, let's see, this is h. But this time, the distance will be your y coordinate. So the distance, remember, is p. So you have HP here for the focus. Now for the directrix, suppose you get first the point on the parabola. Let's say this is measured x. Supposedly this will be measured y, but since your graph starts here, so you'll have y minus k. Okay, if you project a line perpendicular to the directrix, so the line of intersection, the point of intersection here is the same with the x coordinate, so you'll have x. But your y coordinate should be the same, the negative of this, because the distance is the same as this. So you'll have negative p. Okay, let's use the definition again. So the distance of this is the same as this, and this is the same as this. Although my drawing is not perfect, so it doesn't look like they have the same distance, I'm sorry. But the distance from this to this is the same as from this to this. So you'll get, I'll take the distance formula. Let's have x sub 1 minus x sub 2. So this is your x sub 1 minus x sub 2 plus This is your y sub 1. So you have y minus k minus p squared equals the distance from this to this. So I have x sub 1 minus x sub 2 plus y sub 1 minus negative p. So I'll have plus p here. Okay? So let's simplify this equation. I'll square both sides so the square root sign will be removed. I'll remain with this term. So I'll have x minus h squared. But I will simplify this term. So this becomes y minus k squared minus 2p y minus k. So just a basic special product plus p squared. This becomes 0. This becomes a basic special product. So I have here y minus k squared plus 2p y minus k plus p squared. So p squared will be cancelled because they have p squared both sides. This will also be cancelled. So you will have, what you left here is this. So x minus h squared. If I'll move this term to the other side, this becomes positive, and they have the same term here. This one is positive, this is negative, but if you move this, you'll get positive, so you'll get 4p in total. So 4p y minus k. Now this is actually an equation of a parabola if you have a vertex at point hk. You have a point hk here, so this is now the equation of your parabola. And this type of parabola opens up as what we have illustrated earlier. So your 4p here matters because if the value of your 4p is positive, of course this is up like this, positive. But if you get the value of 4p as negative, then your parabola opens down. Same derivation, what happens when your parabola opens either up, right, or left? Same derivation, you just get y minus k squared equals 4p x minus h. So if this is positive, this is right. If this is negative, this is left. That's it. Okay, so we have now derived equations of parabola. So let's have these again. Let's have x minus h quantity squared. You'll have 4p y minus k. So this is either up or down. And you'll have y minus k squared equals 4p x minus h is either left or right. So for the case for up and down, so you'll just have to check on this. If this is positive, it's of course up. Otherwise, it's down. And you'll have to check this. If it's positive, then it's right. Otherwise, it's left. Okay. 2y squared minus 16x equals 0. Okay. First things first, we will have to check on the equation if we're really dealing with a parabola. So in order for us to check that, you just have to check. There are two variables only, the x and the y. So you'll have to check that only one of the x and y is of degree 2 and the other one is of degree 1. Otherwise, you're not dealing with a parabola. It could be a circle or other conics. So this time, when you check on the equation, there's only one variable that bears the degree of 2, which is the y. So The x here is 1 degree, so you can think that this is already a parabola. So let's reformat this one. I can write this equation as 2y squared equals 16x. Or I can have y squared equals 8x. So looking at this format, it looks like this. So you can have y minus 0 squared equals 8x minus 0. So which means this is your h, this is your k. So the center of your parabola, the vertex of your parabola is 0, 0. Your 4p here is 8, which means the length of your latus rectum is 8 units. And if you divide this by 4, your p here is 2. Therefore, since this opens to the either right or left, then it looks like this. This is already positive, so it opens right. Now, your vertex is 0, 0, and the distance is actually 2 units away. The focus is 2 units away from the vertex. So this, your focus is 2, 0. And of course, your directrix is 2 units away from the left of your vertex. So somewhere here is your directrix. Therefore, the equation of your directrix is x equals negative 2. So if you're going to plot this, you'll have if you're going to plot this on the graph, you'll get this. So this is your vertex. 1, 2, this is your focus. Now the length of your latus rectum is 8, so therefore 4 on the left, 4 on the other side of your latus rectum and 4 on the other side of your latus rectum. So this is how your latus rectum, because it opens there. So 4 here, so 1, 2, 3, 4. So this is the end point of your latus rectum. 1, 2, 3, 4. So another end point of your latus rectum. So this is somewhere 2, 4 and 2, negative 4. So your directrix is 2 units from the left of your vertex. So 1, 2. So this is the equation, the line of your directrix. So this is x equals negative 2. And this is your parabola. So you just connect that one and this. Just connect that one and you'll get that. That's it. Let's say, okay, so this time let's consider another example of a parabola. So let's say, find an equation of a parabola having one of the endpoints of the latus rectum is, let's say, 0.31, and its focus is at point, let's say, 3.7. Let's change this x coordinate here. Let's change this to 1. Let's change this to 1. And the directrix passes through second quadrant. So let's imagine this way. How does your equation look like? So you'll have the focus found on point 17. So let's say this 1, 2, 3, 4, 5, 6, 7. So this is your focus here. One of the endpoints is found in 1, 1. So this is your length. I mean the endpoint of your latus rectum. So the distance here is 6. So 6 units. So you'll have another 6 units here for another endpoint. So this is probably 6, 1, 2, 3, 4, 5, 6. So this is 13. So 1, 13. So simply the length of your latus rectum is 12. Okay? So observe that your directrix is somewhere here, which means your vertex is in between the directrix and the focus. So your vertex is somewhere here, which simply implies that the equation of your parabola, your parabola opens to the right. There. Okay, so since it opens to the right, all you just have to do is to get the vertex first. So remember your LLR, or the length of the latus rectum, is 12. So your P, if you divide this by 4, you get 3. So the distance from the vertex to the focus is 3 units. Therefore, 3 from going to the left is -2. So your vertex is -2, 8. I'm sorry, 7. Because they have the same y coordinate with the focus. 7. So your directrix is 3 units from the vertex. So that's -5. So therefore directrix is at the equation x equals -5. So 1, 2, 3, 4, 5. So this is your directrix. So your vertex is here. So your parabola should be like this. Okay, that's it. Now how to get the equation? So since it opens to the right, so your format should be like this. 4p x minus h. So you already get the vertex, so you just simplify this. You just simply substitute this. So you have -7 squared. Your 4p is 12, so you have 12x minus -2, so x plus 2. So it's up to you whether you have to simplify this to get the general equation of a parabola, or just go with this. So that's a standard equation of the parabola. Well, either of the two, they're actually the same. That's it. Okay, let's consider another tricky example, which is I have considered putting this problem in the book I'm currently making. So this is the problem. Find an equation of the parabola where the vertex is at quadrant 1. The line segment from the focus perpendicular to the directrix at point 1, 2 is parallel to the x-axis, and the length of the latus rectum is 12 units. So how do we imagine that one? So if you have the focus here, you have the line segment. Let's say the line segment is parallel to the x-axis. So this is your x-axis here. So you have a parallel line segment. Where is your 1, 2? So somewhere here is your 1, 2. So here. So this is where your directrix. So the tip of this is the focus. So this simply tells us that this parabola opens to the right. Excuse me. The length of the latus rectum is 12 units, so we're given already the latus rectum. So solving for P, your P is 3. I think this is the same as the problem we've answered earlier. I'm sorry. I haven't thought of the problem earlier. Like, I just thought it now. Okay, so this is P equals 3. So therefore, mm, this is your 1, 2 here, the intersection of the line segment and the directrix. So 3 units from here. So this is 1, 2. 3 units to the right is so this is actually 4, 2. And this will tell you the vertex. Another 3 units is actually your focus, which is 7, 2. So you already have the length of the latus rectum. You already have the vertex. So 6 here. So let's say this is 6 units here, 6 units here. So this is how your graph looks like. So the equation will be y minus, this is your h, so 4. I'm sorry, 2. Your k is 2. So you'll have 12 x minus 4, so squared. So that's the equation of your parabola. That's simple as that. Okay, so let's consider another example here. We're asked to find an equation of a parabola with vertex 5 units away from the x-axis found on quadrant 3. And its directrix is perpendicular to y-axis at point 0, 8. So let's imagine the graph here. So this is your x-axis. Found on quadrant 3 is somewhere here. And it's 5 units away from the x-axis. So your directrix is perpendicular to 0, 8. So somewhere here is 0, 8. So this is your directrix. So somewhere here is 5 units. So somewhere here is your vertex. Which simply tells us that our vertex is, we don't have the h here. It's quite general. But our k is 5. So therefore your p is 3 because the distance from the vertex to the directrix is 3 units. 5, 3. 5, 8. So 3 units. So therefore, the length of your latus rectum is 12. So this will also tell you that it opens up because the vertex is here. Your directrix is here, so somewhere there. Because the focus is somewhere here. So since it opens up, so you'll follow this formula. Therefore, your final general equation of your parabola is this. X minus h equals 4p. So your 4p is already 12. Y minus, what's your k? 5. Negative 5, sorry, it should be negative 5, so plus 5. So that's it. So this is now the answer. So whatever the value of your h you'd like to put it here, they're all the same because the question will just ask you in general form. That's it. Okay, so that's all for now. Thank you so much for watching. So we're done so much with parabola. So what we've done so far on this analytic geometry series video is the circle as one of the conics and this parabola as one of the conics. So up next will be ellipse as one of the conics. So I want you to subscribe down there on the subscribe button, and you can also like the video. So see you next time. Thank you.